Hello and welcome to our continuing series on routing, Huawei routers. Today we are going to continue with OSPF adjacencies. OSPF adjacency is part of the neighbor formation process. So what we are going to see is that when neighbor process have been successfully achieved using the hello packets, there are some routers that will proceed into forming an adjacency. I'm saying some because not all of them transition into forming adjacency. And OSPF routers cannot exchange link state information before they establish adjacency. So what you're saying is before OSPF routers can start exchanging link state information, they must establish adjacency. The adjacency must be established. So after neighbor discovery using hello packets, we looked at that in our last video, and I have attached a link to that video so that you can recap on it. Some OSPF routers will start the process of forming adjacency. Not all routers form adjacencies. We are going to look at network types in our next video, and we will see circumstances in which adjacencies are formed and circumstances at which adjacencies are not formed. For this video, we are going to look at the process of forming adjacencies. So we looked at this diagram in our last video, the process of forming neighbor. Remember, we had neighbor, the three states of neighbor. It can be down when this router has sent a hello packet, but it hasn't received any hello packet. So at that time, it will be down. And then it can transition to init state. Init means it has received the hello packet, but in the list of neighbors, it did not see its own router ID. And then it can transition to two-way, when now it receives a hello packet, and that hello packet in its list of neighbors, it receives its own ID. We looked at this in our previous video extensively. So this is a recap that a successful neighbor formation can be two-way. Two-way is a stable neighbor formation from down to init up to two-way. Two-way is a stable. So once you have two-way, some routers will go into forming adjacencies and some will be stuck at two-way. We'll look at that in our next video. So after neighbor is formed, neighbor two-way is formed, some network topologies will conduct what we call a DR/BDR election. We have given this one as the zeroth step because not all network topologies will perform DR/BDR election. Not all of them. The some topologies will have this election. If that topology is eligible, if those routers are eligible for DR/BDL election, that election will be performed after two-way has been achieved. After two-way has been achieved. Because I see this question in some exams, when is DR/BDL election is formed, is conducted. If that topology qualifies for DR/BDL election, it will happen after the two-way state. So the first step of forming adjacency is called Exstart. In the Exstart state, remember we had those packets. The packets we had hello packet, and the second packet was database description packet. So in the Exstart state, router A will send a database description packet. And we say database description packet contains a brief of all the link state advertisements it has. Like for this router, it already has a network 1.1.1. So we expect the database description to contain that LSA, a description of that LSA, not the complete information about that LSA, but a description. We use an example of movie trailer. It can have a trailer of that. But in the Exstart state, we do not have any LSA description. The purpose of Exstart state is to establish what we call sequence numbers for acknowledgement, because if I send a database description to this router, how do I know that it has actually received it? A database description does not have an acknowledge mechanism like we have for link state updates and requests. They have a link state acknowledgement, but database description does not have an acknowledgement mechanism. So they use sequence number. So the purpose of the Exstart is to determine who will have control of these sequence numbers. So at first, this router A will send a database description that does not contain any LSA. In the Exstart, the database description packet does not contain any LSA. So it will only have a sequence number. The sequence number is arbitrarily set. And then there are some bits. I stands for initial, M stands for more, and MS stands for master slave. So it will say that this is my initial DD, is the first one I'm sending. And of course, I'll send more because remember, I have LSA that I'll send to you later. But for now, let's first establish who has control of the sequence numbers. So I have more, and it will assume to be the master. So the MS bit will be set to 1. And then in a similar fashion, RTD will send its own DD. The same DD has sequence set to arbitrarily. And it also has initial beta set to 1 because it's the first one it's sending. And then it has more because it has a network that it will have to inform router A about. And then it also assumes to be the master. So the question is, this router A assumes to be the master and router B assumes to be the master. So the master means I'll take control of the sequence numbers. So how to determine to break the tie, because this one has assumed to be the master and this one has assumed to be the master, is that they will look at the router ID. Whichever has the highest router ID becomes the master. So this one has the highest router ID. Remember, the packet header will always have the router ID as part of the sections. So it will look, this one will look and see, this router will look and see, look, the one that has sent me this DD has a higher router ID. So I will relinquish my master. So I'll be slave. So the MS bit will be set to 0. So that is the Exstart process, determining who is the master. So the master will be router D. So router B will be the one taking charge of the sequence numbers. So that is the Exstart. Then negotiate who becomes the master and who becomes the slave. Now that you have determined that this is the master and this one is the slave now will send another DD with the network, with the LSA, the trailer, remember the trailer, the network description, a brief description of the network. Which sequence number will it use? It will use the sequence number that was set by the master. You see now how the sequence are used? No, it will set a DD and it will use the sequence number that was set by the master. And of course, this is not the initial DD because it had already set this. And then it will say there is more. And then the MSB will be 0 because it has the lower of these two routers, it has the lowest router ID. So the one with the highest router ID becomes the master. And then a brief description of the LSA that it has. You see, a brief description of the LSA that it has. The LSA here is 1.1.1. So we have, for simplicity, I just said LSA header for network 1. Okay. Similarly, this one will send its own DD because it has a network. It will inform now. So it will send the network. It knows about this network. So it will send a DD that has a description, a brief about that, the 2.2.2. And it will use another sequence number, you see. It will use another sequence number. So it will say, I have, this is not the initial one because already I had sent another one here. And I have more I'll send you because this one is not zero. I'll have more. I'll send you if it has more. If it doesn't have, it will set this bit to 1. And then the master is 1 because this is the master. The master slave bit is set to 1. And the description, the trailer I'm sending you about is for network 2. So this state where they're exchanging the actual description of the LSAs of the networks they know, it's called an exchange. It's called exchange. Now, the database description packets have the LSA headers. And the headers here is a brief description of that particular network. See the difference between Exstart and Exchange. DD here have LSA headers. In Nextstate, the DD do not have the LSA headers. All right. So the next step now is router B will, as it's sending this, the database description for the network it knows, it will also send a request for this LSA header because it realizes when this router A send the database description for LSA header network 1, it didn't have that network in its own database, link state database. So it will send a request, you see, it will send a request for that particular network 1.1.1. Then we'll expect RTA to send now the full movie, not a trailer now, the full information about that network in a link state update. Link state request for missing LSA, that I'm missing this LSA in my link state database. So kindly send it to me because you have indicated you have it. So I'm missing it, send it to me. So now RTA will send a complete information about that particular network. This is now complete, the complete movie. Not the trailer. Here it was a trailer. Now this is a complete movie. And then RTB will send an acknowledgement for that particular update once it receives it. So in analysis, acknowledgement. Then remember that also this router B also sent a DD about a network 2. And then RTA looks and realizes I don't have network 2 in my link state database. So what does it do? It sends a link state request for that particular network. It will send a link state request for network 2.2.2 and it will use ID. We look at the structure of LS request, you will see that it has an ID. It has an ID. So it will capture that ID and say, I want that particular network. So then the router B will send an update, the complete in an update. And then similarly, router A will acknowledge in link state acknowledgement that I have received network 2.2.2. This process of sending the link state requests, getting an update, and sending an acknowledgement, when all of them are done, when all of them are completed, all the link state for all the DD we had received with all the headers, if you have got all the information, all that process is called loading. This process of link state request and receiving an update and acknowledging. You will do all that for all the networks that are missing. So that is called, all that process is called loading. It's called loading. When it has, the routers have received all the headers that were stated here, and I have received all of them, the complete all of them, the router will be in full mode, that it has indicating that it has received all the missing link state advertisements. That will be the full mode, and it's a stable state. It's a stable state. It's what we expect to find when we say display OSPF peer. Now, from this diagram, the process I have described, it seems as if a router the OSPF router has to wait for the exchange process to be completed before the loading starts. You can see. But this one, I did that because I wanted to explain the process. What normally happens in in the live network is that the exchange and the loading, they happen together. Let's see how that one happens. We are saying the loading can happen together with exchange. So we have said our two-way. As a two-way, if it qualifies for DR stroke BDR election happens, and then we have our Exstart where we are determining who is the master and who is the slave. Now we will have this sending the DD, the first DD, and it will attach the sequence number of the master. Remember, we said it will use the sequence number of the master. And then it will say, here is one because there is no more, sorry. It will say, I know about network 1.1.1. This is the brief information about it. So what will happen before this one send its own database description, it can decide to request immediately for this particular network that doesn't have. So it sends an immediate link request. You see, link state request sends an immediate one. And then as it's sending that request, it also sends its own database description for network 2. You see, it also sends its own description. Then, sorry, then because router A has received a link state description describing this network, it realizes it doesn't have. So what it will do first, it will send an update for this network it sends because it will give an update for this request, you see. So it sends the full network that it was requested for, sends the full network. At the same time it's sending the full network, it can also request for this DD it received, you see. It realizes that I don't have network 2. So let me request for late. At the same time, it will acknowledge this DD because using this sequence number, it will request, you see, it requests and say, and you realize this one does not have a header. Probably this one M should be, it's 0 because meaning there is no more. This is the last DD. I don't have any other network apart from network 1.1.1. So more bit is set to 0. You see, there is no more. So I have acknowledging, and that's why I do not have a header, an LSA header, meaning that I have exhausted all the information I have about my link state database. I have exhausted. That's why more here is set to 0. Remember here more was set to 1, meaning there is more. But after sending 1.1, the more was set to 0 because it's the last one. It's the last one. That shows that the exchange phase has been completed. You see, that's how you know the exchange phase has been completed. You see, because more bit is 0. That's how you know the exchange bit has been completed. Even though inside here, you can see elements of loading because there is link state request, there are link state update. You see? So RTB continues and sends an update because it was requested for an update to set a complete, give me the complete information about this link state because I don't have it. It sets an update of 2.2. And then what do you expect RTA to do? To acknowledge. And also it's this one RTB when it's sending, it will also send an acknowledgement for receiving this request. So it will send a link state update that I received 1.1 successfully. And then also this one, RTA, will send a link state acknowledgement for receiving 2.2. So it will send an acknowledgement. So as you can see, inside here, this process from 3, It is intertwined. There is the loading phase, this loading phase, and this exchange phase where we have DDs being exchanged, and we have loading where we have link state update, link state acknowledgement, and link state request happening. So we are saying the exchange and loading can happen interchangeably together. So once that one is completed, that we have received all the link state information that we do not have, the router will transition to full. So after exchange is done, loading is done, the router transitions to full. So let's see that one practically. So I had some configurations here that I had done for this particular network. So we are looking at this network. This is RTA and this is RTB. I'm doing some packet capturing here so that we can see the update. So when we look at RTA, the router RTA, I hope we'll have those. Yes, we have some messages here. So as you can see, this router transitions to init. You see init, and it tells you the previous state was down. It starts from down, goes to init, and then to two-way. We looked at this in the last video. So immediately, this network does not have DR or BDR election. So immediately it goes to Exstart, as you can see. There is Exstart here. It goes to Exstart, where we are exchanging DDs without the LSA headers. So there is DD without the LSA headers so that we can determine who is our master and who is our slave. So once that negotiation is done, it tells you that the negotiation for master-slave is done, it transitions to exchange. You see where now we'll start having our LSA, our DD containing information about LSAs. So after that one is done, after the exchange is done, we have the loading. You see, we have the loading state. Loading. So loading is completed, loading is done, we transition to full. And that's what we expect to see when we do display OSPF peer. So we expect to display OSPF peer. Let's make it brief so that we don't have a lot of information about it. You see, we have the full state. So let's look at the structure of the packets. So remember here is the hello packet that is used to form that neighbor relationship. So I've received a packet from 192.168. That is router A. This is router A. Dot 1 is router A and dot 2 is router B. So here I already have a hello packet, and in the list of neighbors, it has 2.2.2. So that means it's already in the two-way state. So immediately router 2, which is RTB, sends a DD. You see, let's look at this DD. This DD has it sets an arbitrary sequence number. You see, it sets an arbitrary request number 725. And if you look at the bits, it has set initial bit to 1 because it's the first one. And then more bit, there's more of this coming. And then it assumes to be the master because this is the Exstart. In the Exstart, everyone assumes to be the master. So the master MS bit will be set to 1. And the sequence number is arbitrarily set to 725. Arbitrarily, that one doesn't. The first one, when they send the first one, the initial bit, this sequence number will be arbitrarily. Then similarly, router A sends also its own DD that doesn't have LSA. If you look at these DDs, they do not have LSA headers. They just have sequence number and these bits. You see, it's also its initial is the first one it's sending, and the more bit is set to 1, meaning there will be more coming. And the master bit, it also assumes the master bit to be, it also assumes to be the master, and also sets its own arbitrary. Then it realizes, wait, the DD I received previously had a higher router ID than me, because if you look at the headers, look at the headers here, the headers has a router ID. You see, there's router ID here, 1.1. So it realizes the ID where I received from is higher than me. So I must be the slave. That's how they negotiate. I must be the slave. So it sends another one that says I'm the slave, you see. Sends another one that says I'm the slave. Let's look at it. Let's forget about this header. Let's look at this DD description. It says this is not the initial one because I had already said this one. And then there will be more, there will be no more coming. This is the last one. And then the master slave bit is 0 because I am the slave. You see, sends it to 0. And then it has a header. You see, it has an LSA header. This one did not have an LSA header if you look at it. But this one has an LSA header telling you the exchange phase has started. And then look at the sequence number it's using. This is a sequence number that was used by the master. If you look at it, it's a sequence number that was used by the master. So it will use it because I'm the slave. I will use the sequence number that was set by the master. You see? And then this is why we are saying that the loading phase and the exchange phase can happen together. So immediately R2 receives, RTB receives a link state, a database description about link state. Remember, this has this link state header, this one, about 1.1.1. Immediately it receives that. It receives, you see, this is a DD that has a link state header saying, I know about 1.1. And then you see it has a link state ID. So RTB will use this link state ID to place a request. You see, it uses that to place a request and says, give me this link state ID. You see, give me that. I don't have it. Give it to me. I don't have it. And then it will also send its own database description about network 2.2.2. You see, and it will set a new, because it's a master, it will set a new, it will increment the sequence number by 1. And in that, it will say, I know about network 2.2.2. This is the description, brief description. I have a trailer for network 2.2.2. Then it will also set, so this, the router B now will send an update for this request, complete update. If you look at this header, it doesn't have a lot of information. The LSA header on this description, it doesn't have a lot of information. If you look at the LSA header here, just it doesn't have a lot of information. It has just the age, do not age, false, meaning don't remove it from the network, length. You see, it doesn't have a lot. Doesn't have a lot. These are different ones. Forget about this. It doesn't have a lot, just have some brief description. But now, when it sends the update, you see this update it's sending because it was requested. Now it's sending the update. If you look at the update, the LSA update packet, you look here in details, you will see that it has more information. It has flags. This one you didn't see in the description, the type, and you can drill down to the type, different types. You see, it has a lot of more information than what was carried in the description. You see, it has a lot of more information. So this one is the complete information about that LSA. DD has a brief, but update has the complete information. I hope that one is clear. And then it also sends a request because it receives a database description from 2.2, from 0.2. It received this database description and then realizes I don't have it. So it sends a request for it as well. So you see, and also sets a a database description for the acknowledgement of this one, because it's the slave. It has to acknowledge that I have received. So it will use the same. It will use the same that DD sequence that was set by the master, because when it was sending this, use 726. So it will use the same. And then the more bit is 0, meaning I don't have any more to send. And you can see it doesn't have an LSA. That marks the end. Because there is no LSA coming from RTA, sorry, that marks the end of the exchange phase. You see, exchange phase. Exchange phase ends there. Forget about these two. Now it's time for RTA to send an acknowledgement for receiving network 2.2. You see, this is an acknowledgement for 2.2. And also RTB to send acknowledgement for receiving 1.1. I hope that one is clear. How the loading and the exchange and the exstart, they come into play. So that's how they come into play. So as a summary, we are going to look at the stable states. What you can have when you display OSPF peer brief, because we are still looking at neighbor formation. So what are the stable states of neighbors? So you can have first state is a down state, is a stable state. You can display OSPF peer and you will see down. It's a stable state, but it's not desirable. We do not want our OSPF routers having a down state. So if you find such an occurrence, maybe the other router has not been configured for OSPF or a link is down. So you have to troubleshoot. And then Init, where we said that it has received a hello packet, but it hasn't seen its ID in the list of the neighbors. When you display OSPF peer, it's very difficult for you to see this state. It's a transition state. It's not really a stable state. Then two-way, when it has received a hello and it has seen its own ID in the list of the ID of the router of the neighbors of that particular packet it has received. This is a stable state and it's okay. You can have a two-way state. So then you have Exstart is not a stable state. It's difficult for you to see this when you display OSPF peer brief. It's a transition state. And so then you can have the exchange and the loading. We say this one is for negotiating. Exstart is for master-slave negotiation. Exchange is where they exchange the database description packets. And then loading is where you send the request, the link state request, the updates, and the acknowledgement. Then when everything has been received, all the missing link state information has been received, the router transitions to full. So these are full is a stable state. When you display OSPF peer brief, you find full. So our desirable state is two-way or full. If you see any other thing, if you see loading, for example, you wait, it will transition to full. If you see exchange, you wait, it will transition finally to full because it will wait for the exchange to be complete and the loading to be complete. So thank you very much for watching this video. The next video will be on network types, and we will see where we have DR/BDR elections and where we do not have them. Thank you very much. Keep on tuning into our videos, and please subscribe so that you can get notified when we produce another video like this one.